Greetings all. I thought I'd go over 4 different problems that will definitely come in handy for the test over this chapter. In the first problem, we have a satellite in orbit well above the Earth's surface, and the question is, what is its weight? You're given the radius of the Earth, the distance above the surface of the Earth, where the satellite is located, and you're given the mass of the Earth. And you will notice, just for the record, right here, that if you multiply 108 kilograms by 9.8, this would be the weight of the satellite on the surface of the Earth before it's launched into space. Now, one of the ways we can attack this problem is over here on the left, where I show you a derivation very similar to the way I derived the ideal gas law way back in chemistry. And that is, we say that at some distance d1, my satellite is going to have some weight. We'll call it weight 1. And because it's an inverse square law, that weight will be proportional to the inverse of the square of that distance. Now, that same satellite will have a different weight, weight 2, at a different distance, distance 2. And again, that is an inverse square law. Now, in order to get rid of these proportional signs and make them equal signs, we need to put in a constant. So there's my constant. The next thing I do is solve both equations for k. Solve both equations for k. And now I have the transitive property of equality. If A equals B and A equals C, then B must equal C. And that's what I state right here. If I rearrange my terms, I get equation number 1 in the red. Now it's time to plug data in. So on the surface of the Earth, we have to have one distance. This is the radius of the Earth from the center. And I want to show you something very important. Common mistake students make. Back up here a little bit. Notice that this is in kilometers. This is in meters. And meters is one of the fundamental units of newtons. Remember, a newton is a kilogram meter per second squared. So in order to use newtons, my all distances must be in meters. So coming down here, if I have 10 to the 4th kilometers, I'm going to have 10 to the 6th. That's up here. I'm 10 to the 7th. 10 to the 7th meters. This is already in meters, and this is already in meters. So now I'm adding meters to meters in the numerator. Notice that this is the radius of the Earth plus the distance above the Earth. And that's because it corresponds to the weight at that distance above the Earth. On the surface of the Earth, its weight is 1,058 newtons. Remembering it's an inverse square law. The second mistake that is often made, let's switch to a different color here, is forgetting to square, because it is an inverse square law. Now when you plug your numbers in, you find out that at that distance above the surface of the Earth, the satellite will have a weight of 42 newtons. And that makes sense, because if the weight on the surface of the Earth is over 1,000, we would expect the weight at this distance above the surface of the Earth to be substantially less. I should also mention that we can further simplify this equation by recognizing that the mass of the satellite doesn't change, regardless if it's on the surface of the Earth or way out in space. So since force of weight equals mass times gravity, the masses cancel, and you could have used this equation as well. Now, another way to do this problem is to take Newton's universal law of gravity, which says the force of attraction between any two masses is equal to the product of those two masses and the distance between them squared. And the proportionality constant is Newton's universal law of gravitational constant. So here's G. Here's the mass of the Earth right here. Here's the mass of the satellite given into the problem. And here is my radius of the Earth, and it's squared. And when we plug our numbers in, we get a little over 1,000 newtons, which is the same thing as its mass times the acceleration due to gravity on the surface of the Earth, which is 9.8. And I showed you that up here. 1,058, 1,060, to round it off to 3 sig digs, same answer. Now, at the new distance, at over 10 million kilometers above the surface of the Earth, once again, there's G. Here's the mass of the Earth, doesn't change. Here's the mass of the satellite, doesn't change. But now we use the distance from the center of the Earth, which is the radius of the Earth, 6.375 times 10 to the 6th, plus the altitude above the surface of the Earth, which is even more. Don't forget to square it. And we get the same answer to 3 sig digs that we did up here. Different ways to look at the same problem. Now, on the test, there are a number of multiple choice questions like this one. It says, assume that the two circles above represent two planets. So maybe we could call this planet number 1, planet number 2. And the larger planet has twice the radius that the smaller planet has. How much more will an object weigh on the surface of the larger planet compared to the smaller planet? Now, some things to remember way back from like the first assignment that we did over the summer, at least some of you did it over the summer, and that is that your volume is proportional to the mass. Okay? Surface area, because it's an area, is going to be proportional to the radius squared. So volume, of course, is a three-dimensional thing. Area is a two-dimensional thing. Now, remembering these two equations, the question is, how much more will an object weigh on the surface of planet 2 than on planet 1? By what factor? Now, at this point, I encourage you to pause and see if you can figure it out. And don't resume until you have forced yourself to make an answer. Test yourself. All right, we're back. So, if my radius is 2 times greater, 2 cubed means that my volume is 8 times greater. And if my volume is 8 times greater, then the mass is going to be 8 times greater, because volume is directly proportional to the mass. Volume is the function of an object's mass, assuming a uniform density throughout. And we also know that the force of attraction is directly proportional to the mass. Let me remind you of that right here. This force of attraction is directly proportional to the masses, because they're both in the numerator. Now it's inversely proportional to the distance between them squared. Well, if we are twice as big, that means my area is going to be 4 times greater, and therefore this 2 squared is 4, and that's in the denominator. Remember, this is an inverse square law. So you double the radius, and you're going to have an effect of 4 times less the attraction. So it's 8 times greater because of the mass, 4 times less because of the doubling of the radius, which means that the satellite will have, or the object, excuse me, will have twice the mass. Now we have one more problem. How many times greater or less will the escape velocity of a rocket be from a planet with a mass that's 3 times greater than the Earth and a radius that's 3 times greater than the Earth? And again, remember that volume is proportional to an object's mass, and it's also an inverse square law because of Newton's universal law. Also, because my typewriter could not do a 1/2 in the, my word processing could not do a 1/2 up there in the exponent at the time I typed this up, this equation and this equation do the same thing. Oh, I know I wrote it like this on my word processing in Microsoft Word, and that is because I couldn't do a square root sign over the radius and the gravity. Remember, this is that escape velocity that we derived when we talked about a vertical circle. It has the greatest speed at the bottom and the smallest speed at the top. Remember that from previous on this very handout. So I'll pause right here, and you should pause and then force yourself to declare an answer, think it through, and then resume this screencast and see if you got it right. So stop your screencast at this moment. All right, we're back. So here's the escape velocity of the planet. Here's the escape velocity from the Earth. And remember, this planet is 3 times greater in mass and 3 times greater in radius. So what does that look like? Because it's 3 times greater in mass, and I'm going to rewrite this equation. Because it's 3 times greater in mass, it's going to be 3 times greater in its gravitational attraction. And because it's 3 times farther away, that means that there's my 3 times the mass, because the volume is going to be 3 times greater. And this is my inverse square law. If it's 3 times the distance in radius, you've got to square that. And so we get, so we get 3 times 3 over 3 squared. 3 squared is 9. 3 times 3 is 9. 9 divided by 9 is 1. 1 to any power is going to be 1. And so it turns out that on this new planet, on this different planet from the Earth, that's 3 times greater in mass and 3 times greater in radius, we get the two equaling each other. And I think I said this wrong earlier. This is the radius right there, and this is due to the gravity right there. I think I said that backwards. So figure it out, and hopefully that's the answer you got.